Tes. All right, let's start. So if you're not aware that I posted iClicker question. Basically, the iClicker is what is the electric field of a single charge? So you can do that, and you can. So it's basically it's a gift. Anyone is it's a gift for people who come to the class on time. And then you can still enter your answer here. But some announcements. One is I made a mistake when I set up your iClicker. So the iClicker in the previous grade book, the points were wrong. I have fixed it, but I haven't sent you another email because otherwise you will get so many emails from me. I plan to send the same email every weekend, okay? But it will be fixed. And then don't follow the grade book on Canvas. Follow your grades in my email. So that's iClicker. Second, there is one perusal due today and perusal due on Monday. If you haven't finished reading perusal for today, you can still do it after. The penalty for not doing it before the class is minimum. And then what else? Any other thing that I missed? How was the lecture, the recorded lecture? Oh, thank you. It was, it's difficult in case you haven't done, you haven't recorded yourself for 50 minutes. It was late, it was cold, I was hungry. But I'm glad that some of you find it bearable. Second, how was the recitation? Huh? That was good. Okay. How about you? So the class has started here. Guys. All right, I'm gonna stop until the class is quiet. Excuse me? So let's, please avoid talking to your friends. So some of your parents, some of your friends, not some of your parents, some of your friends' parents actually work 3 jobs, so their kids or so your classmates can go to ASU. So if you don't do it for me, do it for your friends' parents, okay? All right, so I'm gonna stop the iClicker. What are you guys talking about? I mean, like, all right, so this is from the recorded lecture. Basically, recorded lecture was initially I intended to give a lecture about electric field, but I think the first half of it was on something else. I don't remember exactly. But electric field, what is an electric field? What is an electric field? Anyone still remember? It's basically the force per test charge, okay? Is electric field real? No, okay. Electric field is real, but it's not physically real, but it's real. It's hard to explain, meaning there is nothing, it's not like I emit like bullets or something, or I emit liquid. But if you have a test charge, then you can feel the presence of the field. Okay? So electric field is different than, let's say, a flow of water, but we will use that analogy today in today's lecture. And I think your perusal also use the flow of water as an analog of electric field. So basically, flow of water can exert force if you swim against it, or if you are in a river, let's say. Similarly, electric field can exert an electric force if there is a test charge nearby. Right? So the answer, so if we have positive charge, the electric field will look like this. Will point away from the charge, and the number of the arrows, the number of the lines, you need to be consistent, but there is no consensus. Meaning, one line, there is no consensus that say, I don't know, like is equal to 1 coulomb per, or 1 coulomb per K or something. K here is the constant. Okay. Or if you read other books, K is equal to 1/4 pi times permittivity of the vacuum, which is epsilon 0. For negative charge, the field points into the charge. So if we have a test charge here, I think your book used the symbol Q prime. And Q prime is always, the magnitude is always, you can think of Q prime as +1 coulomb. There is a plus here. If there is a test charge, it will be pulled into the negative charge. So we did this in the lecture. So in the next few lectures, we will talk about two more concepts. So on Monday, we will talk about work and electrostatic potential energy, or U, and also we will talk about voltage. So these four concepts look very similar. K, you see Q in all of this, Q prime for F and U. The force and the fields, they are vectors. The other two are scalar. So you need to know the difference between all of this. And the reason why we introduce you to these concepts, because some of these concepts are easier to calculate than, let's say, if you choose different concept. What I mean by concept is parameter. Okay. So one, if you, let's say, use Gauss's law that we will discuss today, you will arrive to the question much faster instead of, let's say, calculating the field or E. Good. So I went over your perusal, and a lot of people are confused about Gauss's law. So I'll try to do it. I'll try not to rush. But one thing that I will not do is do proof. This is not a proof-based class. And for Gauss's law, especially, it takes, I can do it probably in 40 minutes. So it's not going to be on the exam, and we will not go over it today. The proof, but we will do a lot of Gauss's law today. Oh, and one thing this is still a recap. There are, I think, 3 iClicker questions. Those are not graded. 3 iClicker questions in the YouTube lecture. Those are not graded, but those are somewhat, in terms of how tricky or how difficult those iClicker grades, they are above average for this class. So this is my way to encourage you to know how to do those iClicker questions. Okay. And one thing that I mentioned in the lecture was vector addition. Make sure you remember how to do vector addition. And this slide shows, again, there are many physics simulation online. This is one of them. So for vector addition, you can, let's say we have vector A, or electric field over one charge, let's say. And we have another vector here, and let's say it's larger, the magnitude, and also point differently. Okay, so maybe I need to do 2D. So let's say vector A from the first charge look like this. From another charge look similar. And I hope you still remember that for vectors, it doesn't have to be vectors. All you need to care are the magnitude and the direction. So the exact position doesn't really matter. Okay? So I can place it here, I can place it somewhere else. But let's say if we decompose this vector, right? So vector B has Y component, and let me clear. Vector A, let's decompose vector A. It has Y component and X component. And let's say we want to add a different vector, then you can just sum those components. And if you forget your vector addition, then you can ask your TA, or me, or your LAs. Are we good? Okay. There must be, sum. So okay, so the sum of A, which is A plus, the sum of A and B, which is A plus B, is this vector S. So basically, vector S is the X component of A plus the X component of B. I'm moving my cursor here, plus the Y component of X, of A, sorry, the y component of A and the y component of B. So you get this. The reason why this one is shorter than the y component of A, because the y component of A is like points towards the opposite direction than the y component of B. This should be straightforward to most of you. If not, then you have to work harder than your friends. Okay, so I have this short iClicker question. These are two vector A and vector B are identicals for both option A on the left, apologize, capital A and capital B. The question is which A plus B has a larger magnitude? Okay, and I'll give you, sorry. Is that clear? The question is, A plus B. That's the question, okay? And then the answer is either A or B. And I give you 30 seconds. So 20 more seconds. And you can discuss it with your friends, but we have to move fast today. 8 more seconds. 4, 2, 1. What is the answer? Which one is larger for A plus B? B. Good. So 90% of you got it. So option A, which is capital A, the magnitude is 0 because they point towards the opposite directions and they are equal in magnitude. So it's like 1 minus 1 is equal to 0. Any question? Okay, good. And then in the recorded lecture, we study dipoles. Basically, the fields of a dipole. So a dipole is defined as one negative charge and one positive charge, and they are equal. And this is the field. The reason why the field looks like this, because of vector additions from the field due to the charge on the left, plus, when I say plus, is a vector addition with the field produced by the charge on the right. And this is not a dipole. This is two negative charges. If you sum the fields, and I show a simulation online that you can play, you can try, and if you do it really carefully, or if you find a better simulation than that, you should let me know. You will get this field. The reason why there is no field in the middle, because the field due to the charge on the left points to the right, and the field due to the charge on the right points to the left. So they cancel out. All right, this is not an iClicker. And then we ended with infinite plates, basically. And all of you, any question about infinite plates? Infinite plates basically literally means a plate that is very large. And I think in the lecture, I say that the field is uniform. Let's say the top has pluses and the bottom plate has negative charges. So, and because of that, the field will point down. And the iClicker question, I think, asks you about, what was the iClicker question? iClicker question asks you about the movement of, or the direction of the field. And the answer is the opposite of this, but this is a common problem in physics. I'm just curious because I didn't explain the problem really well. Anyone knows why the field should be uniform in infinite parallel plates? Why the field in between has to be uniform? What I mean by that, if the field location 1 is the same as the field in location 2, why it has to be the case? So again, the plates, these two plates are infinite. So if you have infinite plates, whether you move, well, right now they are different position, right? So that's what you can think of it as something that is caused by the field. But you can think of it as something that generates the fields. So if you have a parallel plates, and they are very large, or they are infinitely large, and let's say you move the plate, I don't know, by 100 meter or 200 meter, the plates still look the same. So if something that causes the physics looks the same, then whatever measurement also should be the same. So that's the reason. I'm not going to ask you this question on the exam, but this is just for you. In case you made a mistake in the future in doing the thing that you need to do, if you understand it, then you can ask yourself at the end, does it make sense? If it doesn't make sense, then you need to check anything that you do in life. So I understand maybe some of you are not planning to be physics majors, but there was a student who were sitting in this class before and switched to physics major, and he turned out to be the best student in the department. He won Goldwater scholarship. He was a student in my lab, and there was another student who stays in pre-med. She also won a Goldwater scholarship. She also joined my lab. Okay. Any question? So those are recap from last lecture. Apologize for taking too much time for recap. So in case my recorded lecture was super unclear, I decided to not take a change and do a long recap. All right, so let's start. Let's now talk about something that is amazing, which is Gauss's law. And every year, many of you are confused about Gauss's law. I think that's how to pronounce it, Gauss's law, instead of Gauss' law. So your book did a good job in pushing the analogy of water flow or liquid flow and electric fields. They are not the same, of course. And then some of you may say, oh yeah, of course they are not the same. One is water, the other one is electrical phenomena. But what I mean by they are not the same is water, there is something that flows. For electric field, there is nothing that flows. But if you have charge, the charge fill it. In water, water flows. If you, let's say, throw a rock or you swim, you will feel the water flow. Right? So let's try to stick with this a bit crooked analogy and push it even more and arrive to Gauss's law. I'm going to be nice to you, so let's start with the equation. So this is the flux, electric flux. And I think your book used this symbol. I start using another symbol. So basically what this is trying to say is that E perpendicular is the magnitude of the vector E. E is the electric field that is perpendicular to A. Okay. And then this one is E, and then I made the surface perpendicular. I mean, they're the same thing. And what is amazing with Gauss's law, this one is equal to the enclosed charge divided by epsilon naught. And then if you read other books, they may use different notation for epsilon naught. So this one is epsilon naught equal to 1 over 4 pi k. So I just move epsilon naught from right-hand side to left-hand side. And similarly, k from left-hand side to right-hand side. So this one equal to q enclosed divided by, no. So 1 over epsilon naught is equal to 4 pi k. Honestly, I don't remember which notation that your book used. And if I made a mistake, you should correct me. Okay. All right. So this is Gauss's law that you need to solve homework problem. All right, so let's use the analogy. Let's stick with the analogy of water. So the flux is basically for water, for hydrodynamics, is the number of water that enter into a volume. Right. So how to calculate that? So you know the mass density of water, which is rho. All of you still remember, right? Rho is mass density. Okay. So number of, and water at a unit of time is equal to mass divided by V. V is the volume, which is rho, times the volume divided by time. The volume is the speed of the water, and this is speed. Times area. So speed is length divided by time. So this is length divided by time times area is volume divided by time. Anyway. So this one is equal to rho times speed. This is speed here, small v, not volume, times A. So, and then you may define this into, I don't know, funny V, let's say. So basically the number of water that flow per unit of time. So rho times V is equal to a funny V. So what I'm trying to say is that this funny V is similar to the fields. It's the amount of force that a field can generate if there is a unit charge. So the it's basically flux of, let's say, hydrodynamic. So now the question is, what happened if the area is tilted? This area here is tilted. So you have this liquid flow, and then the area, I'm not going to draw 3D, I'm just going to draw or I'm gonna keep it the same as in your textbook like this. Okay, so this is area, and this is in in front view. So the flux is less than if the area is perpendicular. So what you need to do is you can do the same thing, but the area that you want to calculate is the area that is perpendicular from the flow of water. Is that clear? Or do you want me to just show you the formula and do practice problem? Okay. And then if you remember the trigonometry, then this area here is actually a cosine. So this one is A cosine theta. Yeah. Let's use theta instead of phi, because flux is phi. So realize that I just changed the notation and nothing happened. Nothing bad happened. We're still alive. This is just a name. This is the same like your parents gave you name like, I don't know, Holden, Nathan, or Muhammad. You can change this to alpha if you want. I just don't like, I know your book used phi. The problem is flux, the symbol of flux is also phi, so I don't like that. And the last case here is if this is a water flow, which is the analog of field, and the area is parallel to the area is parallel to the flow. So what is the amount of water that enter the area? If water flow through this and then flow through this direction, and the area is parallel with respect to the flow of water, what is the number of water that enter this area? 0, right? 0. And you can use the same formula. So theta, if theta is equal to 90 degrees, then cosine theta is equal to 0. And theta, let's say, equal to 0 degree, which is here. Cosine 0 is equal to 0 degree, 1. So we're going to use this analogy and hopefully that helps. Any question? All right, so back to Gauss's law, which is upstairs. So Gauss's law says that the flux is equal to E. If you know calculus, it's E dot A. If you don't know, then you can view of it like this, times Q enclosed. So let me just write it down like that. The flux is equal to, or the E times the area that is perpendicular from E, or we just derive the trigonometric function that we use is cosine theta. Your book used phi. And this one is equal to 4 pi k q enclosed. Okay. Or I prefer this notation. It's just easier to see, nicer to see. Any question? So this is really bizarre because E can be really complex. So why we ask you to learn Gauss's law? Because it's really amazing. That's one thing. Because E can be really complex, right? If you want to solve for E, you can see, let's say, for the case of 2 charges, E looks like this. And then it will be a nightmare to solve E. Let's say here, what is E at this position? I don't think you want to calculate that here. But if we define an area like this, right? When I say area, this is actually a 3D cross-section, a 2D cross-section of a 3D phenomena, 3D system. So this is an area. I know it's only a circle, but this is area. Then what is the flux here? Somebody with yeah, you. Yeah. Yes, you. Yeah, what's your name? Yes, you. Yeah. What is the flux here? Okay, sorry. I was talking to the other person. Yeah. What is the flux in? Yeah, you. It's okay. You shouldn't laugh because next is you. Okay. Oh, okay. So, yeah, good. Because I haven't defined what is Q enclosed, but all of you have read Perusal. Q enclosed is the charge inside the area. So what is Q enclosed here? Two pluses, right? I know there is no unit. Let's just call it 2. So what? This is 1 coulomb. So this one is 4 pi k times 2. So it's really simple. So it's really easy. If you try to use E and A is easy. A is 4 pi times r square. But E, they are not the same. And then you have to calculate all the cosine terms. Okay? I know this is probably a big jump. Let's start with a simpler case. What is the simplest case in physics or in electromagnetics? Which is a point charge, Q, and let's make it positive because that's the simplest case instead of 2 pluses. And the question is, what is the flux here? What is the electric flux at this position? So we can use, okay, so first, the electric field is always perpendicular from the surface. Right, this one is perpendicular. So what is the cosine of okay? The cosine is 0 degree, but they are perpendicular. It's because this is how we define theta. So flux is equal to what? E, which is K times Q divided by R squared, right? This is E, or maybe I need to do it step by step. Like E times A, and they have to be perpendicular, so I just put it here. So what is E, the electric field of a single charge? What is the electric field of a single charge? 90% of you answered correctly in the beginning of the class. It's K times Q divided by R squared. What is the area of a sphere? Area of a sphere. What is the area of a sphere? 4 pi r squared. Oh, I'm not going to give you this formula on the exam. You should know cosine, sine, area of a sphere, volume of a sphere. You should know that. But I will give you all this, the rest of the formula, like Gauss's law, electric field, etc. Right? And this one cancel. So we end up with 4 pi times k times q. Okay. So the electric flux is 4 pi k times q. So we use this step here. Let's say we use this one. So electric flux is also equal to 4 pi k times the charge inside the enclosed volume. Right? I don't know why. What is the amount of charge inside the volume? Yeah, Q. Yeah, or 1. You got it. You understand what I'm trying to say here. So this one is equal to Q. Previously, it was 2Q or 2. I think previously it was 2. Now it's Q. So it's equal to 4 pi times Q. I hope this one, I hope you can see that using Gauss's law, we arrive to the solution faster. The reason why it's not much faster, because the system is so simple. But like, let's say questions about inductor, or if I move the charge, or if I have 3 charges, 100 charges, it will be much faster using Gauss's law instead of calculating the field individually. Yeah, good. I see, good. So I'm using the definition of the angle that your book used. So the cosine, okay, so again, we're a little bit behind again, but first, I'm going to answer your question. So the reason why there is angle there is because of in math or in life, we need to describe a surface. Okay. How to describe a surface? Let's say this is your surface. How to describe the surface here? First, you need the area, right? You need the area. But stating the area alone is not sufficient, because the surface can be like this or can be like this. So mathematicians develop a way to define a surface by adding a surface vector, which is perpendicular from the surface. So if the surface like this, the surface vector will point perpendicular from the surface like this. If the surface like this, like what I'm doing right now, then the surface vector will point like this. And this theta is the angle between the surface vector, every surface vector, and the field. The field is parallel with the surface vector. So theta is equal to 0 degree. So cosine theta is equal to 1. Is that good? Yeah. Oh, for this, if you have a sphere, it's perpendicular. I see. This is because the surface, this is why I had to introduce the surface vector. So surface vector is perpendicular from the surface. And the angle is the angle between the surface vector and the field, not with the surface of the surface. You know? That's the reason why the angle is a little bit, could be the source of confusion. Excellent question so far. Any other question? Yeah, sorry, so I wasn't being clear. So that angle is the angle between the vector, surface vector, which is perpendicular from the surface. So let's say this surface here, this is the surface vector, and the field also points like this, right? You know that if there is a charge there, the field at this position due to the charge will be exactly aligned with the local surface vector. So the theta is actually 0 degree. This is a matter of definition. And it makes sense. Yeah, what do you think? So that's the magic of Gauss's law. Even if the surface is like the size of a galaxy or really tiny surface like this, the flux is the same. It's independent. So that's the, and this is because the field follows inverse square law, and the area of a sphere also follows, well, it's proportional to distance square. Okay. And then typically, so this is like if somebody emits like water, let's say, or bullets. So let's say if the Q is here, then it will be very tricky to perform this calculation without calculus. But let's say Q is off center. But since you know Gauss's law, then all you need to do is just sum the charges inside the surface. And then you will end up with the same answer. So that's the power of Gauss's law. And that's the reason why the book, your book, makes a big deal of the area. The area has to be what? The area has to be close, meaning there is no holes. You cannot have an area. So I know you understand this, but I'm gonna, so this one is actually 3D surface like that, right? And you cannot have a hole here. If you have a hole here, then the amount of flux that you calculate depends on the position of the Q. So for all of this, the area has to be close. So in some books, they even put sigma here. The reason why I put sigma, because in one of your homeworks, you need to calculate the flux in inside a cube. So in that case, there are 6 surfaces. In order to completely enclose a cube, you need to add 6 surfaces. One of you asked this question this morning. You should refill yourself. You left? Okay. Any questions? Okay. So the flux is independent of the surface. Okay. So in the next, throughout the lecture, we will do 2 Gauss's laws. One is for charge or electrostatic or electrostatic. Second is for magnet. And the formula looks identical. Not identical, almost the same. You just need to replace electric field with magnetic field. Okay. All right, so let's do this. I clicker real fast. What is the electric flux of a point charge capital Q? I think the answer is still on the whiteboard. So I give you 30 seconds. 15 more seconds. All right. All right, so the answer is A. So the answer is here. Not because the answer is on the whiteboard. So you replace small q with capital Q, but because that Q is inside the area. Okay. All right, so this is a question that relates to your question. So I'm going to give you a minute because it takes a while to read the question. What would happen to the electric flux of a point charge Q if our sphere has a radius of 2r instead of r? Will it increase or will it decrease? The formula is like this, and we have just spent 15 minutes discussing Gauss's law. Okay, so I give you 1 minute. You can discuss it with your friend. Oh, some of you need this. Okay. All right, 10 more seconds. Okay, so the answer is A. Right. Any questions so far? So finally, I still have 1 more minute. The surface doesn't have to be smooth. Okay, in one of the questions in your homework, the surface is actually a cube, but it has to be enclosed. It has to be a closed surface. So I don't know, maybe I need to invent another symbol, another subscript like this. Okay, it doesn't have to be smooth, but it has to be closed. All right, so any questions? If not, I'll see you on Monday. Have a nice weekend. Yeah, I can. I'm listening.